Hey everyone, how goes it? And welcome back to Computer Science 146. Today, we're going to be talking about searching, sorting, complexity. Oh my! Let's first start with some very common algorithms in computing. These are called searching algorithms. And for argument's sake, here is our problem. So given a sorted array of integers, we need to develop an algorithm that returns true or false, depending on if a target value was found in that array. One approach to this is we can do what's called linear search. So basically, if we start from index 0, we scan through every index, and if we find that value that we're searching for, we return true, but if we don't, we return false. For example, let's say that we're looking for the target value 11, and we're going to go ahead and start at index 0. So we just compare the values at that index. So 5 is not equal to 11, move on. 6 is not equal to 11, move on. 7 is not equal to 11, 8 is not equal to 11, 9 is not equal to 11, 10 is not equal to 11, but 11 is equal to 11, and we return true. So obviously, this is a way that we can implement a searching algorithm. Now, let's go ahead and see this in code. As you can see here, we've already set up the project and created the class search algorithms. What we're going to do is just develop these one at a time and see how they work. So first of all, let's do linear search. Public static. Reason why we're doing this static is so we could directly call it from the main method. So public static boolean, and we'll just call this linear search, where we're going to pass an int array A and an int target value. So then we know the best friend of an array is a for loop, and all we need to do is for int I is equal to 0. So we're going to start from index 0, while I is less than a.length I++. If we discover a at index I is equal to our target, then we can return true. However, if we get outside of this for loop and we have not returned true, this means this target value was not found in this array A, so we can safely return false. Let's now apply this to our example. So let's go ahead, I'm going to set up an int array, and we're just going to call it array. And I'm going to set it to the exact same values that was in the example, so it has to be a sorted array, and the values that were contained was 5, 6, 7, 8, 9, 10, 11, and 12. This both constructs this array and assigns each one of the values one at a time. So this is index 0, 1, 2, 3, 4, 5, 6, 7. Now, let's see if this works. I'm going to call system.out.println, and then I'm going to call the method linear search, given this array and our target value 11. Let's see if this works. Sure enough, it returned true because the value 11 was in this array. Now, this is one way that we can search for values in an array. But are there other algorithms that also search? Let's take a look at a different algorithm for this version of search. This algorithm is called binary search. The main idea about this one, if you're given a start and an end index, what you do is you find that middle value. Then you compare that middle value to the target value that you're looking for. If the target value that you're looking for is less than that middle value, then only look on the left-hand side of that value. And alternatively, if the value that you're looking for is greater than that middle index value, then look at the greater side, the right-hand side of that array. Let's take a look at this example. If we're looking for, again, the target value 11, what we do is we start from the range of 0 to 7. We know the midpoint equation is start plus end divided by 2. So if we want to get the middle index, we do 0 plus 7, which is 7, divided by 2, which is 3. Now this assumes that we're doing integer division, and every time we do integer division, the decimal point is cut off. So this would be 3. Now we compare the value. 11 is greater than 8. So the thing is, we understand that this is a sorted array. As we've already checked this value, and we know that everything to the left of this value has to be less than, well, we don't need to check these other values. All we need to do is check the values up here. So then we restart, but this time instead of starting at index 0, we start at index 4. Now to get the midpoint, we do 4 plus 7, which is 11. 11 divided by 2 is 5. Now with this one, 10 is greater than 11, so we just look at this side of it. Now we get to this point, where we have to look at this range. 6 plus 7 is 13. 13 divided by 2 is 6, and 11 is equal to 11, so we return true. Let's take a look at this in code. Now once again, here we have our linear search. We're going to go ahead and develop the binary search. And the way that we're going to do this is we're not going to implement this in an iterative way, in other words, using a for loop. We're going to do this in a recursive way. Public static boolean binary search. And we are searching an array A for some sort of target value. And also with this one, we need to know the start index and the end index. As this is a recursive method, we have to worry about its halting condition. So if the start index happens to be greater than the end index, then we need to return false. It was not found. Now that we've taken care of that halting condition, we need to find that middle index. So we're going to call this int mid is equal to start plus end divided by 2, the midpoint equation. Now that we've calculated that, if A at this middle index is equal to our target, we return true. However, if that's not true, else if A at this middle index, let's say that this value was greater than the target. Now this means we understand that this A has to be sorted. Now if this middle index value was greater than the value that we're searching for, we only need to search the lower half, the smaller values. So this means we're going to return the recursive call, binary search, using the same array A, looking for the same target. We're going to start from the same place, but instead of ending at this original end index, we're going to end at the midpoint, but minus 1. We've already checked the value at this midpoint. It was greater than this target value. So in this case, start from the same place, but stop in the middle, minus 1. Now, if the midpoint value wasn't equal to, and the midpoint value was not greater than, it can only be less than. So in this case, we're going to return binary search with the same A, the same target. But this time, we need to start from the midpoint plus 1. The target value that we're looking for was greater than that midpoint value. So starting from that middle value plus 1 all the way to the end, is that in there? Now to test this one out, we're just going to edit this and we're going to do binary search. And this time, we need to start it from index 0 and end it at array.length -1. Running this, we do find that the value 11 was in this array. Now, if we were going to start comparing these two different implementations of a search algorithm, well, which one is more efficient? First, we need to know what efficiency even is. So we are going to produce desired results with little to no waste. Basically, a well-organized algorithm will prevent wasteful use of resources. Now, resources in terms of computing, we're always concerned with time and space. Relating that to the hardware, think of time as being the commands run by the CPU and space being the amount of space used in memory. But again, how do we measure efficiency? Even relating this to the hardware of a computer, we recognize that algorithms do not require computers. So, how do we measure something that doesn't require a computer? It doesn't make sense to time them. So then we start looking at this idea called complexity. Complexity classifies these computational problems based on inherent difficulty. We then use complexity to relate problems to each other, and we view complexity based on time and space. In order to evaluate the complexity, we use what's called asymptotic analysis. Now, this is a way that we can describe the limiting behavior of a mathematical function. And as a reminder, limits in math are a value that a function approaches as an input approaches some value. It's like when you see a limit where n approaches infinity. And so using asymptotic analysis, we can then explore time and space complexity. We use this mathematical notation called big O. Now, big O is a theoretical upper bound of an algorithm, and you can think of this as being basically the worst case scenario. Big O is defined as if we have two functions, f of n and g of n. We can then define big O of f of n is equal to big O of g of n, where the n belongs to the set of real numbers as n approaches infinity. Now, this is such that the absolute value of the function f of n is less than or equal to an m, which is a big constant, times the absolute value of a g of n for all n that's greater than the initial value of n. What does that even mean? Let's back up slightly. We are referring to complexity, and we're going to use this big O notation in order to describe complexity. Now, if we go back and we recognize this theoretical model of a computer, where we basically have some input being passed into the computer, it computes, and then yields some output, this is how we should start thinking about these functions in relation to what we're doing. Like, for example, if we're looking at time complexity, so for a given amount of data n, how many operations will the algorithm take to complete? And similarly, for space complexity, for a given amount of data n, how much space will the algorithm require to complete? So when you're seeing these functions, think of n as the amount of input, the amount of data. Now, combining this together with our big O notation, big O time complexity is for a given amount of data n at most. How many operations will the algorithm take to complete? Similarly with space, for a given amount of data n, at most, how much space will the algorithm require to complete? When we start assuming at most, this means we are viewing the worst case scenario. So what would the case that would cause the most operations for this algorithm to complete? Or what is the case that would require the most space to complete for the space complexity? Looking at the definition of this function once again, we assign a big O as a means to describe the time or space complexity given some input n as that n approaches infinity. But more to the point, always recognize that big O is an inequality. This means that the function g of n does not have to be exactly equal. It has to bound it. Everything that the f of n describes has to be below the curve of that g of n. Now, speaking of that, we can take these functions and plot them on a graph. That way we can more easily see what's going on here. What we can do is take one of the axes and correspond that to the amount of data, the n. For argument's sake, let's say that this is the amount of data, the elements that are part of, for instance, this array. Now, the other axis might correspond to either the operations or the amount of space. This type of big O is looking at the time complexity where, given this amount of elements here, how many abstract operations have to happen so that the algorithm completes. Now, looking at this, you can start seeing how we start applying that big O complexity. So basically, if we're looking at a function, what we always want it to do is be below the curve of the big O complexity that we're describing. So for example, you can say that the function f of n is equal to n is equal to big O of n. Now that's simply because here's big O of n and it's just a straight line. This is equal to. So we can say that yes, you can say f of n is big O of n because f of n will never go above this line right here. It'll be exactly equal to it. Now, alternatively, you can use the same function, f of n, and describe its big O as being n squared. Now, while we can say this, recognize that the f of n is this line, n squared is this line. This does qualify as a big O, but this is not a tight big O complexity. Ideally, you want the big O's function to be close to the line that you're describing. But as long as it's greater than or equal to the function, then you're good. So this would include if you had this f of n, which could be a quadratic. You can simply describe that as big O of n cubed, because n cubed is always going to grow larger than this function. And also similarly, you can describe f of n squared as being n factorial, which this one basically bounds almost anything. Now the thing you can't do, if our f of n was described as n squared, which is this line, we cannot say that it is big O of n, because this line is not below that line. Similarly, n factorial cannot be described as big O of n squared, because this line is way above this line. You also can't describe the function f of n as being the constant value big O of 1, and also you can't describe the function 2 to the power of n as being big O of n. The big idea is recognizing that big O is an inequality. As long as the function that's in the big O is always greater than or equal to the function that we are describing, then we can call it the big O complexity. Now, also in computing, there are some very common big O's that we see a lot. Like, for instance, big O of 1 is some constant value. Big O of log n is called a logarithmic function. Big O of n is linear. Then you have linear arithmetic n log n, quadratic n squared, exponential where you have 2 to the power of n, and these can be considered pretty bad algorithms. And n factorial, if we're describing an algorithm whose complexity is that's a really bad algorithm. Think of it this way. If we were to apply the value 100 to n, imagine what this looks like with each one of these functions, especially 2 to the power of 100 and 100 factorial. Now let's take all of these concepts and start applying it to our examples. That way you can see how we can use a big O function to describe the complexity of an algorithm. Now, for argument's sake, Let's go ahead and take a look at the two algorithms that we have previously described. First one is linear search. So basically what we have here is if we have this array of size 8, our worst case is trying to find something that doesn't exist inside this array. So let's pick the value 13, which we can see is not in this array. Now, in order to confirm this, what we have to do is check every single value. So 5 isn't 13, 6 isn't 13, 7 is not, 8 is not, 9 is not, 10 is not, 11 is not, 12 is not. Now we're outside the array and it's not found. So if we assume in this example the array size is 8, that means our input is 8. It took 8 checks in order to discover that this value wasn't there. We can describe linear search as being big O n. So once again, if we had an array that was size 1000 and we're trying to look for a value that's not in that array, it's going to take 1,000 operations to confirm that. Let's apply this now to binary search. So once again, our array size is 8. Well, in this case, what we have to do is find that center value, compare, and then split. So if we start here, we compare it. 13 is greater than 8, so then we split. 13 is greater than 10, so we split. 13 is greater than 11, split. 12 is greater than 13, well, now we're outside of the array, and it was not found. Now, comparing and splitting took roughly 3 operations to determine this. Now, if we assume this array was size n, what is a function that we can use to describe it? Here's the trick. Look what happened to the amount of data that we were examining. We took this array of size 8 and then split that in half. Then split that half into half, and that half into another half. And we keep splitting the amount of data in half every time. The type of function that best describes this is a logarithm. In computing, we specify the log base 2 of n as just simply being LG. So binary search works big O of log n time. Now we have to determine which one was better, which one was more efficient in terms of time. Plotting both of these functions on a graph, this is what they look like. This is linear search. This is binary search. Now the way that we can start examining this, if we have this given input here, let's say it was 10. Binary search only takes this many operations to complete, versus linear search, which takes this many operations to complete. Given the same amount of data, linear search takes more operations to complete than binary search. And so we can safely say that binary search works better. It solves the same problem in less operations. Now, all of this has been fairly weighty concepts, and I'm not going to go into details about how to prove the big O complexities of these things. However, what you can start doing now is looking directly at your code and estimating what the big O complexity could be. Here's some easy steps to follow in order to figure out what the complexity of these certain methods might be. The first thing to keep in mind, if you have any simple statement, like a print, an if statement, a return, that's always going to be constant time, big O of 1. Now, complexity starts increasing whenever you start encountering loops and also recursion. So taking this example over here, what we have are a lot of constants. So the if statement and both of the returns are considered big O of 1. They happen instantaneously. But then we have this for loop. Now we have to start recognizing that this statement inside of here is run some number of times. And the easiest way to see this is it goes from 0 through the entire array. Now, if we assume that the array size is n, we can sufficiently say this for loop is going to run n times in the worst case scenario. Now, we also have this constant value still remaining there. But the thing is, if we basically take the big O of this n and add it together with this constant value, we can just say it's big O of n. Remember that n is a part of a limit. This n approaches infinity. As this n approaches infinity, constant values stop mattering. And also recognizing that in the definition, you have this large constant value m that you can then use to describe all of these extra things. So it's easy enough to say that this is some big O of n. Let's now apply this to binary search. If we were going to do this, then we do recognize that we have a lot of constant statements throughout here. However, we have these recursive calls here. This is where you have to pay attention to what's happening inside the data structure. In fact, these are cutting it in half. The other thing to recognize that only one of these is going to be called at any given time. You're not going to call both because it's an if and an else. Now, as we are cutting these in half, we can describe this as log base 2 of n. And since we can only call one or the other, then we have a bunch of constants added together plus a big O of log n. And once again, log n approaches infinity faster, so the constant values stop mattering. We can just describe this as being big O of log n. In order to measure efficiency, we need to examine complexity. And in complexity, we use mathematical notations like big O in order to theoretically describe the complexity of an algorithm. That way we can compare it against other algorithms. And in the next lecture, we're going to look at more advanced algorithms and more examples of big O. With all that being said, I'll see you next time.